We carry billions of transistors in our pockets, capable of executing billions of instructions every second. Yet when you open a heavy spreadsheet or try to render a 4K video file, that raw processing power can't stop the screen from freezing or the system from failing to respond. These failures are a direct symptom of chronology, the rigid, sequential way our hardware interprets time. Modern computing forces every calculation to move through a strict, step-by-step sequence. This linear mindset is a relic of the 1940s, rooted in the von Neumann architecture. It remains the foundational logic for virtually every device on the market today. This design separates the processor, where logic is executed, from the memory, where data is stored. To communicate, they must pass information across a narrow physical pathway called the data bus. Every data packet is forced to wait in a single file line to cross that bridge. Because information is trapped in this physical queue, processors spend up to 90% of their energy passively idling, simply waiting for the next chronological packet to arrive over the bus. The sheer scale of early machines like the Harvard Mark I explains why engineers prioritized sequential logic. In a room-sized computer running mechanical operations, processing one step at a time was the only way to manage the data. But 80 years later, this chronological treatment of logic makes speed limits and processing bottlenecks a mathematical certainty. This reliance on a timeline physically degrades the system, beginning with the architecture of the data itself, fragmentation. As you delete or move files over time, they leave physical gaps on a linear hard drive. When you save a new file, the operating system awkwardly splits it into pieces to fit those holes, creating more chronological delays as the hardware tries to piece the data back together. Processing limits follow the same linear trap. OS schedulers must slice time into windows, forcing active threads to wait their turn in chronological queues before they can access the CPU. The most severe failure is the infinite loop. When a logical error causes a system to query itself, the processor gets trapped in a chronological echo, repeating the same rules endlessly until the entire system locks up. Raw clock speed cannot resolve these structural failures. Truly seamless computing requires us to move beyond the concept of time and replace it with pure, multidimensional geometry. The self-state registration, or SSR architecture, resolves this by abandoning the rigid, flat timeline of binary ones and zeros. Information in the system is structured using p-adic numbers. Instead of a flat string of bits, data takes the shape of a self-nesting fractal tree. Storage in a p-adic space doesn't require searching for empty sectors down a linear track. When a file expands, the data branches infinitely inward, growing deeper into the existing coordinate. This utilizes a non-Archimedean rule, where every point inside a data sphere acts as its exact center. This allows information to nest perfectly inside itself. This infinite geometric nesting prevents the creation of unallocated gaps, which mathematically eliminates storage fragmentation for the life of the device. How do you move this complex fractal data across a chip without relying on linear queues or copper wires? The SSR architecture replaces electrical signals with multi-frequency optical laser light, which travels natively through a sapphire substrate. The processing pathways are mapped onto a complex multi-hold algebraic shape. This topology creates 336 distinct parallel lanes for data to follow. Instead of pushing data down a wire, the system triggers an instantaneous algebraic rotation of this shape. The data is relocated via structural symmetry, reappearing at its destination without traveling the distance over time. This allows multiple programs to run simultaneously as overlapping rainbow laser pulses. They share the same physical path without ever needing to wait for a clock cycle to hand over execution rights. By substituting physical data travel with structural symmetry rotation, processing latency is reduced to absolute zero. This architecture also provides a native solution for the infinite loops and logical contradictions that freeze traditional systems. SSR utilizes non-associative Octonionic math. When a loop tries to cycle back on itself, the geometric rules shift mid-flight, physically deflecting the error out of the main timeline. A safety net called the Galois Mirror Core runs a phase-inverted twin of the code using light waves. If the code is healthy, the upward peaks of the primary wave perfectly cancel out the downward valleys of the mirror wave, creating a flat, dark line. A logical error or infinite loop breaks this symmetry. The twin waves fail to cancel, generating a bright spike of uncancelled light that punches through the dark mask. This spike acts as a static geometric beacon, allowing the hardware to isolate and mathematically patch the crash in picoseconds without interrupting the user's workflow. We have transitioned from a chronological machine to a geometric one, folding the linear timeline of a computer into a hyperdense, multi-frequency optical shape. This shift enables massive power savings by eliminating block erasures, provides native quantum-safe cryptography, and allows applications to execute concurrently without ever waiting in line. Seamless computing isn't reached through faster clocks, but by transforming logic into geometry. We're unlocking a digital world limited only by the speed of light.